Welcome to lecture 15B of Differential Equations and Linear Algebra, right down here. The main topic that we're going to do in this particular lecture is talk about the foundational theory of what are called vector spaces, with some examples, with some theorems and definitions and that kind of thing. It's our introduction to that theoretical topic, very theoretical. It is important, it's got practical implications for us. Before we do that, we'll also compute a determinant with row operations based on properties I mentioned in lecture 14B. We'll also look at a difference equation, the corresponding dynamical system for that. Based on a reflection linear transformation, we need to find the reflection formula using the idea of projection back from lecture 5B. And we'll be talking about iterating that as we talked about in lecture 14B. That's what's to come. And again, the main thing here is the vector space theory. But let's start with computing a determinant using row operations. We'll do a 3x3 case so it's easy to check. I would like to show you also a 4x4 example, probably in lecture 16B. And I'm going to do it in kind of a fun way there. I'm going to use what are called elementary matrices that can be obtained from an identity matrix by elementary row operations. It's kind of a cool way to do row operations with matrix multiplication. All right, so let's go into the details of this example. So here's my example. Find the determinant of this 3x3 matrix, whose entries you see here, using row operations, using properties from lecture 14B. And I'll describe what those properties are verbally as I do the calculation. So you don't actually have to go back and look at those properties unless you want to. All right, so we're doing row operations. We could go all the way to reduce row echelon form, but we actually don't have to. And it's better maybe not to. We're going to go to just a plain echelon form where we have leading ones or maybe leading non-ones that are also non-zero, and we have zeros underneath them and to the left. We have an upper triangular matrix is what we're after here. So the first row operation I'm going to do is row replacement in two rows actually, the second and third row. I'm going to multiply row 1 by -3 and add it to the row 2 and put the answer in row 2. I'll also multiply the first row by +7 and add it to row 3 to get a 0 there. Put the answer in row 3. I said one of the properties is that row replacement operations, perhaps surprisingly, do not affect the determinant. So the determinant of the resulting matrix will be the same as the determinant of this matrix. Calling the next matrix B. Take the time to double check things, that it's right. Keep the top row the same. If I multiply row 1 by -3 and add it to row 2 and put the answer in row 2, I get a 0 right there that you see right there. -3 times -2 is +6. +6 plus 1 is +7. -3 times 5 is -15, plus -4 is -19. Now multiply row 1 by +7 and add it to row 3, putting the answer in row 3. 1 times 7 is 7, plus -7 is 0. -2 times 7 is -14, plus 2 is -12. And 5 times 7 is 35, plus 3 is 38. Again, those are row replacement operations. The determinant of these two matrices are the same. I will try to get a leading one here in this spot, in this pivot position. My next step is I'm going to multiply row 2 by 1/7. That will change the determinant. If I multiply a row by 1/7, in this case row 2, I'll get a new matrix whose determinant is 1/7 the original matrix. Here's the new matrix. I kept row 1 and row 3 the same. I multiplied row 2 by 1/7. 0 times 1/7 is 0, 7 times 1/7 is 1, -19 times 1/7 is -19/7. This does not have the same determinant as either of these two. Its determinant, in fact, is 1/7 the determinant of these two. Said another way, the determinant of these two is 7 times the determinant of this thing. One more step is all I'm going to do. I'm going to do a row replacement operation by multiply to get a 0 right there. I'm going to multiply the second row by +12, add it to the third row, and put the answer in the third row. 1 times +12 plus -12 is 0. I will get a 0 there. So I will end up with an upper triangular matrix. I also have to do 12 times -19/7, add it to 38 and put the answer there. I will leave it to you to check that you get 38/7 when you do that. That was a row replacement operation. The determinant of these two matrices, C and D, is the same. And they are both 1/7 the determinant of these two. Again, said another way, the determinant of these two is 7 times the determinant of these two. But this one is upper triangular. Its determinant is the product of the numbers on the main diagonal. That was another property of determinants. 1 times 1 times 38 sevenths. So to get the answer we want, multiply by 7. You can write it out this way. The determinant of A equals the determinant of B because I obtained B from a row replacement operation. That's 7 times the determinant of C because I obtained C by multiplying row 2 of B by 1/7. So C's determinant is 1/7 times B's determinant. Said another way, B's determinant is 7 times C's determinant. And then I get from C to D by doing a row replacement operation. It leaves the determinant unchanged. So once again, that's upper triangular. Its determinant is 1 times 1 times 38 sevenths, but don't forget to multiply by 7 at the beginning. The 7's cancel, giving you an answer of 38. 38 is the determinant of the original matrix. We can check this with the cofactor expansion across the top row. Focus on this top row here. I got 1 times 3 plus 8. 3 plus 8 is the determinant of this 2 by 2 submatrix that I get by deleting the first row and the first column from the original. 3 minus negative 8 is the same as 3 plus 8. Minus the next entry is negative 2. Don't forget this minus sign there. Times the determinant of the submatrix obtained by deleting this row and this column. You get a 9 minus 28, like you see there. Finally, plus 5, that's the last entry in the first row, times the determinant of this submatrix that you get by deleting the first row and last column. Its determinant is 6 minus negative 7 is 6 plus 7. So you get 11. Plus is plus 2 times negative 19 is negative 38. 6 plus 7 is 13 times 5 is 65. Combine those and you do get 38. We've confirmed the answer. Okay? Let me show you how to do this on Mathematica right away. This will be the one thing we do in Mathematica for this lecture. Sorry about the extra noise as we've been having recently. School has started and so there's a lot more people around. So A is a 3 by 3 matrix. How do we get a 3 by 3 matrix when this palette only gives you a 2 by 2 matrix? It's a little trick. If you do a control comma, it adds a column, and control return, it adds a row. Control comma is a column because comma starts with C, just like column starts with C. Control return gives you an extra row. Return starts with R, just like row starts with R. So now we have a 3 by 3 setup. I've forgotten what the original matrix was. Let's see, it's entries across the first row are 1, negative 2, 5. Its entries across the second row are 3, 1, negative 4. I'm tabbing over, by the way, to get from one cell to the next. And then negative 7, 2, 3. That's the matrix A. You can see it in matrix form by doing this. And you can take its determinant by doing capital DET of A inside square brackets, and you confirm that the answer is indeed 38. Okay? That's the one thing I want to show you with Mathematica on there. All right, let's move on to the next slide. What happens when you iterate a reflection? We've talked about difference equations, linear difference equations in lecture 14b. We considered dilations, which in math are taken to be expansions or compressions. In everyday life, dilations are always expansions. And rotations. But now let's consider a reflection, and you should be able to predict what's going to happen. I'm going to reflect across the length of the origin. If I do that, if I iterate that function, it just goes back and forth across the same line. And so, in fact, you iterate it once to get across the line and then iterate it again, you should get back where you started. The matrix of this linear transformation, when you square it, should be the identity matrix, and it is. But how do you figure out a formula for the reflection? Well, let's consider an example. So the example we're considering is a transformation that will be linear, I'm telling you ahead of time, across the length of the origin with slope 2. Say it looks about like this. So this is L, it's got slope 2. I'm reflecting across the origin, or excuse me, across that line. So, give me an arbitrary vector, say vector x, whose components are little x, little y. What will be its image under this transformation? Which again, I'm claiming is a linear transformation. It's going to be the reflection across this line. So what you need to do is you need to draw a line from this point to the line that's perpendicular to that line and has a certain distance there from this tip to this line. And then continue the line over here the same distance, still make this perpendicular, 90-degree angle, the same distance from that line that this tip of that arrow is. And that vector that you get by starting at the origin and going to that point right there, say, is going to be the reflection of this vector. How do you find that? You can use the idea of a projection vector. We talked about projection vectors back in lecture 5 and application to forces and work done by forces. The projection vector of x along this line is essentially a vector that's the shadow of that vector if there were light rays coming in perpendicular to the line. Imagine light rays coming in perpendicular to the line of slope 2 through the origin. The shadow of this vector x here would be this red vector here. I'm calling that the projection of x. Sometimes you emphasize it's a long L by putting an L subscript there. How can I obtain the image of x under this linear transformation? This vector over here, t of x. I can obtain it by taking the projection vector and adding this vector to it. But that begs a question, how do you find that vector? We've got a formula for the projection, but how do you find that vector? Let's get into the details now. Okay. We want to find the formula for this function. In other words, we really want to find its matrix. And figure out what happens when it is iterated. Okay, so here's a vector v that is parallel to L. V is not necessarily this red vector, but it is parallel to it. Pretend it's right here. That would be a vector, since this line has slope 2, with horizontal component of 1 and vertical component of 2. Take the vertical component and divide by the horizontal component, you're going to get the slope of the line. The projection formula to project x along that line does involve this vector v that's parallel to the line. This is not a unique answer for v. I could have picked 2, 4 or 3, 6, but this is maybe the simplest vector to pick that's parallel to that line. Yeah, note v is parallel to L. Again, let boldface x be an arbitrary vector. We want to find the image of x under t, as shown in that picture. By drawing an appropriate picture, that picture in fact, it is clear, well, maybe not completely clear. It's clear when you think about it, that t of x is going to be the projection vector plus this vector. I claim that second vector is this one right here. But this vector right there is the projection of x along L minus x itself. Why? Because I claim its opposite that points this direction is x minus the projection. Why is that the case? Why is this arrow right here equal to x minus the projection? Because when I add to the projection vector, this red vector right there, I've got to get x. And when you add this vector to the projections cancel because of the minus sign there, and you're left with x. Say that again. Hope you can see this. This blue vector pointing from here to here is this vector, x minus the projection. Let me write it a little further over to the left. X minus the projection. Why? Because you can see from the picture that when you take the projection and add this vector, you've got to get x. This is the unique vector such that when you add the projection vector to it, the projections cancel, leaving you with x. And the red vector over here is its opposite. This projection minus x is the opposite of x minus the projection. Additive inverse. because it points in the opposite direction and has the same length. Okay, that's the vector that I add to the projection vector. Then when you simplify, oh, more vacuuming. Simplify these two vectors, give you 2 times the projection vector, and then you get the minus x still. What does this work out to be? We need the formula for, dot product formula for the projection vector, back from lecture 5. This projection vector right here equals this thing right here. It's x dot v divided by v dot v times v. I've got the 2 as well that I need to put in front of that, and then minus x. When you plug in x and v, x being little x, little y, v being 1, 2, you should check that you get this, which simplifies to this. Go ahead and pause the video, double check my calculations there. I'm pretty sure I did it right. I did double check it. I'm pretty sure there was no mistake. And hey, that could be written as a linear combination. I didn't do it here. X times the vector negative 3/5, 4/5, plus y times the vector 4/5, 3/5. And so I can think of it as a matrix multiplication. I could think of it as this matrix times this vector. Negative 3/5, 4/5 are the coefficients of x here and here. 4/5, 3/5 are the coefficients of y here and here. That is the matrix that gives you the formula for this linear transformation. If reflections are going to make sense dynamically, when I square this matrix, I should get the identity matrix, and you do. I'll quickly take the time to check this, thinking in terms of dot products. For the upper left entry of the product, I do the dot product of this first row and the first column. Negative 3/5 times negative 3/5 is positive 9/5. 4/5 times 4/5 is positive 16/5. 9/5 plus 16/5 is 25/5, or 1. Got the right answer there. Take the dot product of the first row with the second column to get the upper right entry. Negative 3/5 times positive 4/5 plus 4/5 times 3/5. Those do cancel. Okay, that's negative 12/5 plus 12/5. Same kind of thing happens when you dot this second row with the first column. And then when you dot the second row with the second column, you once again get 16/5 plus 9/5 is 25/5, or 1. That is the identity matrix. The identity matrix times x is x itself. So the dynamic behavior is to go back and forth. Okay? A relatively simple kind of dynamic behavior. I had left myself space over here because I was thinking I was going to draw this picture on the screen, but I didn't. All right, on to our main topic for this lecture. Vector spaces. So this is about to be the most abstract topic that many of you have ever seen in your life. They're also known as linear spaces. Hang with me, it's important. The abstract theory is important. Not going to do proofs today, but I am going to talk about a lot of abstract theory. You can make the abstract theory easier to understand if you think about examples. Examples are very important when you're trying to understand abstract theory. This is a definition. I should have put the word definition in there. Definition. A non-empty set V is called a vector space. Could also have the word real in there. Real vector space, also known as a linear space, if there are two operations defined with respect to elements of V and real numbers. The real numbers are our scalars. These two operations are called vector addition and scalar multiplication, and they satisfy certain properties. Right away, you should think about examples. You do that right away. You could pretend V is R2 or R3 or R4 or Rn even, and the scalars are real numbers. What kind of properties do we want these things to satisfy? I wrote down similar properties when I first talked about vectors, back in lecture 3 or 4, I think. Commutativity, associativity, distributive property of scalars over vector addition, for example. Those properties need to hold here, but there's a bit more. I'm going to show you two sets of properties. They both have 5 properties in them. The first 5 look like this. First one says, if U and V are elements of V, this notation means element of is in, these are in that set. That implies U plus V is also in the set, is an element of. In other words, V is closed under vector addition. I also could have written this line as U plus V is in V for all U in V in capital V. That would be another way to write the first line. But closure is what we're after for vector addition. Second property, commutative property. U plus V equals V plus U. Here I did the for all U and V in capital V. For all, any two elements in capital V, any two vectors, if you want to call them vectors, U plus V equals V plus U. Associative property works. Get this equation for all U, V, and W in capital V. Doesn't matter where you put the parentheses, and in fact that implies you don't even need to put a parentheses in here. When you do put it, you're emphasizing this is done first, U plus V, then W, and it equals the same vector you get when V plus W is done first, and then U. Fourth property. Might seem like it doesn't need stating. And hey, I'm using a backwards E. There exists, existential quantifier. There exists 0 in V. ST means such that, that's shorthand for such that U plus 0 equals U for all U in V. What in the world? What's that about? Isn't that obvious? Well, no, it's actually not obvious in the theory, in this definition, because I need to say there is a zero vector is what this means. There is an additive identity, which we often call the zero vector. It exists in V. There is an element with this property with respect to vector addition. Fifth one is for all U in V, there exists a negative U in V such that U plus V negative U equals 0. Kind of weird. Each vector has an additive inverse. And I do not want to write this as U minus U, though eventually we can. We can define what vector subtraction means, but since I'm not defining what vector subtraction means, I have to write this as, with a plus sign there. The negative sign in front of the U is just to be suggestive of the fact that that's the usual way to think about it. But I didn't have to write that symbol there. I could have just called it V. I could have said for all U in capital V, there exists a V in capital V such that U plus V equals 0. V would be the additive inverse of U in that case. But this notation is suggestive of the fact that we'll often think of the additive inverse as negative 1 times U, though that's a property that needs to be proved. Second group of properties is about scalar multiplication. If U is in V and alpha is a real number, then that implies alpha times U, that scalar times that vector, is an element of V. V is closed under scalar multiplication. The other one was closed under vector addition. The next one is a distributive property. You can distribute alpha across this vector addition. Scalar multiplication distributes over vector addition. There's a second distributive property that looks like this. I described that as scalar multiplication delivers over scalar addition. Here I'm adding vectors, here I'm adding scalars. The alpha is the same up here. The U and V could be different. The U is the same down here. The alpha and the beta could be different. Again, for all U and V and all alpha and beta in R. 9 is an associative property. Scalar multiplication is associative. This notation means do beta times U first, which is really a scalar times a vector, to get another vector. Then multiply that by alpha. This is ultimately 2 scalar multiplications. And it says it equals this, where you do the number multiplication first before doing the scalar multiplication times a vector. Subtle things going on there. These are 2 different kinds of multiplications going on. That's a number multiplication there. These are both scalar times vectors. 10th assumption, 10th part of the definition, is that the number 1 times any vector U equals that vector U for all U and V. In other words, the number 1 is a scalar multiplicative identity of vectors, you could say. 1 times any vector is that vector back. This is part of the definition. In a sense, these are all axioms. These are things we would assume to be true about any vector space. And when we're doing theory about vector spaces, we just work with these abstract properties. We don't have to think about the examples. We can just work with the abstract properties. And it's a worthwhile thing to do. Two main reasons I can think of is it actually, first of all, it actually simplifies things once you get used to the abstraction at least. Abstract math, when you're first constructing it, once you get used to the abstraction, actually simplifies things because you don't have to worry about other things going on. Second reason to do it is it unifies things. You end up seeing that different areas of math are connected. Vector spaces like Rn are going to be connected to function spaces like I've been talking about recently. There's a connection between them. They're both vector spaces for one thing. And so any properties we can prove in the abstract are going to be true for those examples. That's the third reason, efficiency. If you can prove things in the abstract, it applies to all the examples. It is worth learning. Let's quickly go over some examples of vector spaces. Always good to have the examples in your mind as you're thinking about the theory. Okay, it's just beneficial for your understanding. First example, n-dimensional Euclidean space, Rn. I don't think I've called that Euclidean space before, but many people do. After Euclid, who lived a couple thousand years ago, Euclid's Elements, in part, is all about axiomatic geometry, where it's the kind of geometry where with triangles, the angles add up to 180 degrees, and you might scratch your head and say, well, isn't that what geometry is? For sure, shouldn't all the angles in a triangle add up to 180 degrees? And the answer is yes, if you do Euclidean geometry. But there are non-Euclidean geometries where the angles in a triangle don't necessarily add up to 100 degrees. Huh? Look it up. It's based on having different axiom systems to give you different results. But which one is right? They're both right. They're different systems of axioms and therefore different results. Maybe asking which ones is right is the wrong question. Maybe you should ask which one is better, which one's more useful. And the answer is it depends. It depends on what the application is. You want to build buildings, you want to be an architect, you better use Euclidean geometry. You want to send out satellites to orbit the Earth, you better not use Euclidean geometry. Partially because relativity can come into play, and partially because the Earth is a sphere. This is a vector space with ordinary kind of vectors, column vectors, whose components are x1 through xn. That's how I'm thinking of this vector space. And we already know it satisfies all the properties that were in the previous slide. I mentioned that before. And there is a zero vector. The column vectors whose entries are all the number 0. And there are additive inverses. The additive inverse of this would be the column vector whose entries are all the opposites of those numbers, negative x1 through negative xn. Or those are negatives of real numbers, that is negative 1 times each of those real numbers. Any zero vector in a Euclidean space by itself is, as a singleton set, meaning just a one-element set, is actually a vector space by itself. That's a one-element set. It's not the empty set. 0 plus 0 equals 0 plus 0. Adding vectors in here is commutative, for example. There's a zero vector. It's its own additive inverse. Multiplying it by scalars, you can verify those properties, like the distributive property. It's a trivial vector space, one element, but it's worth mentioning. Any line to the origin turns out to be a vector space when you think of it as a subset of Rn. And it doesn't have to be just a line you can visualize in R2 or R3. It could be in a higher dimensional space, and you can't literally visualize it, but you can think of it as all scalar multiples of a given fixed vector. And that'll be a line to the origin. Any plane to the origin. And when I talk line and plane, I'm really talking about, those are sets of points. I'm thinking about the associated position vectors for those points. That'll be a vector space. Lines not to the origin and planes not to the origin are not vector spaces. You might want to think about that. Closure, for example, fails. The zero vector is not in those as well. That fails. Here's one that's a little strange. The set of all polynomials of degree less than or equal to some positive integer n, including the zero polynomial in that set whose degree is, for technical reasons, undefined, is a vector space. Polynomial addition is commutative, for example. You add two, and you also, if you add two polynomials of the same degree, say, you get a polynomial of the same or maybe lesser degree because maybe the highest powers cancel. That's why we need the less than in there. There's a zero polynomial. It acts as the zero vector. You can think of those as functions, or you can just think of them as just abstract symbols that you can manipulate by adding and multiplying by scalars. The set of all functions of the form a times cosine t plus b times sine t, where a and b can be anything. This is an infinite collection of functions of t, where t is any real number. And this is related to differential equations, related to lecture 14a, where we were talking about the undamped harmonic oscillator, and I said what the general solution was. All functions of this form, when you add them to each other, give you other functions of this form. Closure. You multiply it by a scalar, you get another function in this form. Alpha times something like this has the right form. It's some scalar times cosine of t plus another scalar. Oops. Plus another scalar, alpha b, times sine t. It's got the right form still. It's a linear combination of cosine of t and sine of t. Closure happens. If a and b are both 0, that'll be the 0 vector of this vector space. It'll be the 0 function whose graph is a horizontal line along the horizontal axis. What's the additive inverse of anything like this? Well, just negate the a and the b, and that'll be the additive inverse. The set of all sequences of a certain form, like this. A times 2 to the n plus b times 3 to the n plus c times 5 to the n, where n is a discrete quantity, an integer. These are really functions. Sequences are discrete functions. These are things that solve differential equations. These are things that solve difference equations. I have a linear combination of 2 functions here of a real variable t. I've got a linear combination of 3 functions here of a discrete variable n. The set of all n by n matrices with real number entries, where vector addition is matrix addition and vector scalar multiplication is a scalar times a matrix. And things are done entry-wise, which is very analogous to component-wise. So I'm thinking of matrices as being vectors. Actually, I didn't even have to restrict myself to square matrices here. I could have said any m by n matrix. Matrix addition is done entry-wise. So, for example, 1, 2, 3, 4, 5, 6 plus negative 2, 5, 3, 1, 0, 4 gives you the matrix with entries negative 1, 7, 6, 5, 5, 10. I'm adding the matrices. Is it a good idea to add matrices like that? Yeah, though I haven't said why. Effectively, it's really analogous to a 6-dimensional vector. The fact that I'm writing it as a matrix rather than a column vector with 6 entries is sort of just 2 different ways of writing the same vector space, actually. Here are some relatively simple facts that can be proved relatively quickly. I'm not going to prove them because we're low on time, but they should make sense. It's a theorem. The following properties of a vector space V are true, and they can be proved fairly easily with a bit of ingenuity. It takes a little bit of skill with these things to get these proofs. These properties are going to look very trivial. In fact, you might scratch your head and say, well, aren't these obvious? The answer is they are obvious for particular examples, like Rn, but they're not so obvious in the abstract. The point is, do those 10 properties in the definition of a vector space allow us to deductively prove these things and not have to assume that they are true as axioms, not make them part of the definition of the vector space. They are things you would want to be true. You would hope that the scalar 0 times any vector u is the 0 vector. The scalar vector is a vector annihilator. It maps every vector u to the 0 vector. It annihilates it, so to speak. Any scalar times the 0 vector also better be the 0 vector. The 0 vector is a scalar annihilator. Even when alpha is non-zero, you get the 0 vector out. Annihilator just means it's getting sent to 0 under the operation. The scalar -1 sends a vector to its additive inverse. -1u is the additive inverse of u. Negative u. Or maybe it's better to call it the opposite of u. It's the vector in Rn, as that example, that points in the opposite direction but has the same length. You got to prove this. You can't, we're not assuming this is true. You got to prove it. What does 4 say? If 0 prime plus u equals u for some u, then 0 prime must be the 0 vector. In other words, the 0 vector is unique. There are no other vectors that have this kind of property. Line 5 says, if u plus u prime equals 0, then u prime must be the additive inverse of u. The additive inverse of any given vector is also unique. 6, alpha times u and alpha non-zero implies that u must be the 0 vector. The only vector annihilated by the non-zero scalars is the 0 vector. And it was already the 0 vector, so in a sense it didn't get annihilated. And alpha u and u not equal to 0 implies, if alpha times u is 0 and u is not equal to 0, then alpha itself must be the number 0. The only scalar annihilated by non-zero vectors is the 0 scalar. In other words, the number 0. 0 scalar means the number 0. Yeah, so you look at these and like, well, yeah, I mean, this should be true, but we don't want to take them as axioms if we can prove them. That's why we call this a theorem, because we can prove them, it turns out, from the definition of a vector space, when you take those properties essentially as axioms. Here's some fundamental definitions and more facts. A lot of heavy-duty stuff here in a short amount of time. We will go into more depth in lecture 16b. We'll have more time for it. Definition of a subspace. Let V be a vector space, and let H be a non-empty subset of V. It's not empty, so it's got at least one element in it. If H is also a vector space, under the same operations of vector addition and scalar multiplication that are defined in V, then we say A is more than just a subset of V. It's called a subspace of V. It's more than just a subset. It's also a vector space in its own right. So we add the extra word space in there and call it a subspace rather than a subset. A theorem that can be proved based on this definition is that a subset H of a vector space V will be a subspace of V if 3 conditions hold. H is not empty, H is closed under vector addition, and H is closed under scalar multiplication. What this means is that all the other properties in the definition of a vector space can be proved if you know these facts are true. Commutativity, associativity, distributive property can be proved for the vectors in H when you add them and when you multiply them by scalars. Maybe shouldn't be so surprising because H is a subset of V, and V satisfies those properties. So H is really going to satisfy those properties pretty much automatically. There's not much to prove here. The key thing is making sure it's not empty and make sure it's closed under scalar vector addition and scalar multiplication. I've talked about span before. Here's an abstract definition. of span. Let V1, V2 through Vn be elements of a vector space. We could call them vectors. Elements in a vector space V, capital V. The span, I should have boldfaced that, of these vectors is the set of all linear combinations of these vectors. Now, technically speaking, I should define what linear combination means, but I've said that so often recently, you should maybe be able to write down what a linear combination of these vectors is. I'm about to show you. In other words, we define and write a symbol for the span, and its definition is that the span of these vectors is this set. The set of all linear combinations of the vectors. We've got n vectors that were given. Consider the set of all linear combinations of those vectors where these scalars can be any real number. First thing to realize, the span of this finite set is not a finite set, unless all these vectors happen to be the zero vector in the vector space is the trivial example. Then these linear combinations would still give you just the zero vector. In general, this is not a finite set. The C's can be any real number. They are arbitrary real numbers. These are infinite sets. Second thing worth mentioning is that if there's only one V, just a V1 say, then this is the set of all scalar multiples of V1. Which geometrically, if you're in the example Rn, is going to be a line to the origin parallel to V1. If the vector space is not Rn, but maybe a set of functions, you can't really visualize it as a line. Or can you? You can by analogy, but not literally, is what happens. Same with higher dimensional spaces that we can't visualize. If there's two V's that I'm taking the span of, and if they're not parallel to each other, or not scalar multiples of each other, I should say, they're linearly independent, then this span will be, in a sense, a plane, or some analog of a plane in a function space. If V1 and V2 are in Rn, and they're not scalar multiples of each other, then the resulting set will be a plane through the origin. And it does go through the origin, because the C's could all take it to be 0. Here's the theorem. The span of any finite collection of vectors in an arbitrary vector space, in an abstract setting here, is in fact a subspace of that vector space. So to prove this theorem, we would need to use the subspace test. Need to verify that the span is non-empty. That's pretty easy. Need to verify it's closed under addition and scalar multiplication. That's not too hard either. In fact, I'd encourage you to think about proving this. If you work at it hard enough, I think you could prove this. I will probably show you the proof in lecture 16b, but for the moment, take it as an example. This is not easy stuff. We're going to be doing a lot of this theory in lectures to come here. But remember, ultimately relating it to examples, in Rn, for example. We'll be thinking about matrices still. We'll be thinking about row operations still. Row operations help us understand things. We'll be thinking about linear transformations still. In fact, linear operators on function spaces being linear transformations. But the key thing you need to do here to make it through this section of the course is also be able to think abstractly. Think of these as just purely symbolic logical facts that can be proved when they are labeled as theorems. Okay? It can be interesting, even if you really take the time to get into it. And I hope to try to make that clear as we go. Thanks for watching.